No. So we are starting 4.1. We'll spend several days on this. And where we're at in the scheme of calculus, there are three major topics. First major topic, limits. Second major topic, derivatives. Today we're learning our third major topic. And that was anticlimactic. Antiderivatives. We're going to learn how to take a derivative and go back to the original. So this is what this whole chapter is on, antiderivatives. Now, you'll see I've got writing up here because we've got to take time to get the notation down because they kind of switch up some things. We've got to know what they mean. We did this when we first learned derivatives. We spent a while on just the notation. So we're going to spend some time just on kind of getting their idea of the symbols that go with this and everything. And we've got to think through the concepts a little bit. So I'm going to read this first part to you. It says, if f of x is the derivative. Okay, stopping right there, what's already different than what we have kind of already seen? It's not f prime of x. Okay, so if f of x is the derivative and f of x equals 3x squared, find an original function, capital F. So sometimes where we've been so far is here has been the original and we've derived it and it's been f prime of x. Just from this sentence, sometimes the original is going to be capital F of x and the derivative is going to be lowercase f of x. And they always make it where you can tell, I don't know if you've noticed this. I mean, I know you've seen it, but when you take those AP question tests, you know how like in the free response, they give you a ton of information. They're helping like set up the variables and they're helping to like get you in the right mindset. And so they'll always let you know which direction they're going, but this is just another form that we'll have where this is the derivative and then this is the original. Okay, so that's a notation thing. Now let's actually think about what that would be. What would we derive to get 3x squared? X cubed. So the original function is x cubed. What else would we derive to get 3x squared? Oh, jumping right to the end. So like, would you agree x cubed plus 7? Would that still be 3x squared? What about x cubed minus 16? Okay, so then, as Riker said, I'm going to skip that last one. When we go backwards, we've got to account for that constant, and so we're going to put plus c on our answers. Now, we don't have to put plus or minus c. We don't have to say just minus c, because this constant could be positive or negative. So we just put plus c. So that's the thing you've got to kind of train yourself to do when we're going backwards. You've got to remember this plus c, plus c, plus c, plus c. And that's just because any constant that we would derive would then go away. Okay, how are we doing so far? Okay, so we're going to do our plus c's. Okay, let's try another one. And let's look at how they write it. General solution, so that's like how we wrote this answer here. Find the general solution of y prime equals 2. So this is telling you the derivative of y equals 2. Okay, now let's think notation first. If it's y prime, what would be the symbol on the antiderivative when you go backwards to the original? Y prime would go backwards to y, good. Okay, now let's think about the actual number. What would we derive to get a 2? 2x. And then because it's a general solution, what else do we have to incorporate? Plus E. So this is the beginning ideas that we're working with: conceptual, notation, numbers. That would be our general solution. It represents a whole family of answers. An infinite amount of families, an infinite amount of members can derive to get that too. Okay, anything right now to ask? All right, now some more notation stuff. Okay, back when we were first learning derivatives, we learned this was another symbol for derivatives. And this symbol we have used like when we were implicitly deriving, different things. It means we're finding the derivative of y with respect to x. Okay, well, today we just saw that sometimes our derivative symbol can just be f of x. Okay, now I'm going to do some algebra with this. This is dy over dx. It's like a fraction. I'm going to multiply each side by dx. So I'm just kind of manipulating the values, the variables, to rewrite them. This is our derivative. So far, we're just saying our derivative. Well, what we're learning is how to antiderive, how to go backwards. And so when we go backwards, we're going to go backwards from the derivative of y to just y. And to show how this all goes backwards, in comes the squiggle. So the squiggle is the official calculus symbol for anti-deriving. When you see that squiggle, you're going backwards. So I'm going to break this down even more, but this is telling you that the original y function is the antiderivative of f of x. And this guy means that we're in terms of x. And it'll, as we go through this chapter, it'll kind of like make more and more sense what all of those mean also. I don't know. Sometimes I compare this to Spanish or like a language. Like when you first learn languages, you kind of just repeat phrases. And then as you learn more about what those, like the words mean, the phrases actually like mean more to you about what they mean. Same thing here. Right now, we're going to think about this whole thing as an overall like antiderivative. But as we go through this chapter, the placement of all these things will make even more sense as we go. But this is our antiderivative. Okay, so now I'm going to label some parts here. This is telling us to antiderive, but have you also heard of the word, just in passing, have you ever heard of an integral symbol? Integrate, integral, means antiderive. In fact, I'll put this over here. So an integrate, integral, the verb is integrate. That means antiderive. So they're synonymous. So this little squiggle is an integral symbol. Okay, then this object that we're actually antideriving, the thing that we're figuring out what its antiderivative is, this is called an integrand. And this last thing, this tells us what variable we are in terms of. So like, eventually we'll get some trig going, and maybe that'll be like d theta, where theta is our variable that we're in terms of. So that part right there. Okay, now this is telling us to antiderive. I'm going to put an equal sign next to it. When I antiderive, it goes backwards to the original, and I put plus c then. So we antiderive this function. This is our derivative, antiderive. This is our original. And then because we've got to account for the constant, we put that plus c. So this is what we'll just kind of be getting used to, just all the ways that they write the variables. The idea is we're going backwards. Okay, anything just with all of that up there that you want to double check on anything? Okay, now, so far we've done two. We've done the antiderivative of 3x squared and the antiderivative of 2x. Do you imagine it might get more complicated as we go? Probably. So I am going to give you a few rules to help the process out. I'm going from a list. If I'm not going to be like writing all of them out, we're just going to be kind of doing them, learning by doing. But if you want to see them like kind of all technically written out, they're in the textbook. We're going to do them all, but we just won't write the whole list out of what we're going to work on. And so if you kind of remember when you derived, well, yes, you'll remember this. Do you remember how I taught you the long way how to derive? That limit as delta x approaches 0. And then like 5 days later, I taught you the shortcut. Do you remember that time in your life? And that shortcut was the power rule. Well, guess what? It's going to go right into the shortcut power rule for integration. And so I'm going to write this one out, how the power rule works for integration. So we will have our little squiggle, x to the nth dx. So if we are asked to antiderive like x to the 5th, there is a rule that we can follow. Looks like this. So if we're asked to derive x to a power, antiderive x to a power, we add 1 to the power, and then we divide by that new power plus c. So let me show you how that works. Let's just go very simple. X to the 5th. And so what you'll notice, even though it can get annoying and cumbersome, we've got to always include like both of these bookends on here. We need the squiggle and we need the dx. In fact, like on free responses on the AP exam, if you leave one of these off, you'll lose the point values for those. Like even if all of your parts are right beside that, they are very strict about you having both of those bookends written out. Okay, so our power is 5. When we go to antiderive or integrate, we add 1 to the power. So that's going to be x to the 6th. Divide by that new power plus c. And that's our antiderivative. That's our integral. Now, the stage that we're at right now, these are kind of easy to check. If you derive this, you should get back here. So if you bring a 6 to the front, don't those 6's cancel? And then subtract 1 from the power, x to the 5th. So right now, we're kind of easing our way in. You can kind of check your answers. But when we integrate or antiderive, we add 1 to the power, divide by that new power, and remember our plus c. All right, let me do this one. Let's go x to the 314 dx. Okay, so we add 1 to our power, divide by that new power, plus c. There's our integral. There's our antiderivative. Too easy. We need a challenge. The integral of the square root of x dx. Bringing in the radicals now. Okay, so don't forget, the radical is really a power of 1/2. So because it's a power, we can use this power rule. So we add 1 to the power. So that's going to be 3/2. Then we divide by that power, but it's going to look messy. So I'm going to go right into, instead of dividing by 3/2, I could multiply by 2/3. I'm going to do that right away, fix my complex fraction without another step. If it helps you, if you're like, this is too much new stuff right now, I'm going to do this in 2 steps, feel free. If you want to do that, that's fine. I combine 2 steps right there. So instead of dividing by 3/2, I multiplied by 2/3 plus c. All right, now let's try, I'm going to start the constant rule in here now. I'm going to go 3x to the 8th dx. So now this is kind of starting to incorporate another rule in there. And this is where we have the power rule, but we also have a constant. So in almost every single thing we've done this year, there's been a constant rule. And that constant rule says, just tag it along. So I'm going to bring the 3 out. And then x to the 8th, I'm going to add a power, divide by that new power, plus c. And then because we always kind of want to think about if there's ways to simplify, just to kind of practice for multiple choice. And I could divide each of those by 3. So that would be our derivative, our antiderivative. Okay, now let me show you the one that we started the day off with. You were thinking about this in your head, like what was its antiderivative, but we can just use rules. So for rules, that constant can tag along, then take the x squared, add 1 to the power, divide by that power, plus c, and then those 3's cancel, and then this is exactly what you were telling me for the antiderivative earlier. That's what we get. But now, sometimes instead of trying to think individually, if you use your rules, it just kind of always works out for us. Okay, let me show you one like this. Two over x to the 4th. Okay, just like when we derived, we couldn't derive it until that x and the power were in the numerator. Same thing for integrating. We've got to rewrite it first. So if I rewrite it and I bump it up, it'll be 2x to the negative 4th dx. And then my constant can just tag along. Add 1 to the power. Divide by that new power plus c. And then we've got to fix that negative exponent. So I'm going to end up with this as my final answer. So just don't take the 2 down with it. The 2 still staying positive, staying in the numerator, but the x cubed comes down. All right, let me show you this one. What if we were going to integrate 7? Okay, technically, to kind of follow the rules, this is 7 times x to the 0. The 7 tags along, and then we add 1 to the power, divide by the power, plus c. So then in simplest form, that's 7x plus c. So you already did one like this also, because my second question today was, what's the general solution of y prime equals 2? That was a constant, and you guys took it back to 2x. So this is the reason why we can kind of follow the rules to match that up. But when you have just a constant, it goes back to that. Were you doing okay? Any specific questions right now? Okay. All right. Next up, add some pizzazz. So the 4, even though there's trig in there, the 4 is still a constant. Tags along. Okay, then we got to think, what did we derive to get cosine? Sine. And it's still plus c. Okay, so let me show you this thing that sometimes people use, and they'll like write it on their quizzes and stuff too to help them think, because you're going to be working forwards and backwards through trig. So let's think when we first learned trig, how to derive it. If we start with sine, what's the derivative of sine? Cosine. What's the derivative of cosine? What's the derivative of negative sine? What's the derivative of negative cosine? Okay, so we're back to the beginning. That's our cycle. This is deriving. This is integrating. So what sometimes people will do, and sometimes they'll even put that last one on there too. They'll kind of think through the progression of it, and then when they have to go forwards and backwards in their mind, they'll go, which direction am I going? That helps you kind of go. So if that helps you, use it. Like on your quiz, on the AP exam, just kind of jot that down. You'll have your cycle, and you can go back and forth with it. But we've got to think in both directions. All right, next one. Let's do this integral. The integral of x plus 2 dx. So now we have multiple terms. We have a sum going on. Well, just like we've done all year, you just look at each of them separately. When you derive them, you just derive each of them separately. Same idea here. So if I derive x, so that's x to the first, add 1 to the power, divide by the power. And then I want to integrate that constant. So we just talked about constants. That's 2x plus c. Does anybody know why I don't add a c after each term? Yeah. And so if a constant was 7 here and a 3 here, when you add a 7 and a 3, isn't that still just a constant? So we don't want multiple c's. We just want one c when we go to integrate there. All right, let's try one with a little bit more parts. Let's integrate 3x to the 4th minus 5x squared plus x. So this integrand has 3 parts to it. We can just look at each of them separately. So that 3 tags along, add 1 to the power, divide by that power. Negative 5 tags along, add 1 to the power, divide by the power. And then x, add 1 to the power, divide by the power, plus c. And again, none of those numbers simplify. And again, you could derive that to see if you got back there if you wanted to double check your work. Okay, let me show you this one. Okay, so we've talked about before we can integrate, we've got to bump that variable back up to the numerator. When I bump that back up, it's going to be x to the negative 1. Okay, then we add 1 to the power, divide by that power. We can't do that. We can't divide by 0. This is the only time power rule doesn't work. But we know this deep down somewhere in your brain. You know this answer. What did we derive and got 1 over x? Natural log of x. So this is the one time power rule doesn't work, and we already know this one, natural log of x. Okay, there's one thing we have to do differently backwards. I don't know if you remember this, but natural log of x had all positive x values. And just in the process of going backwards and forwards, we've got to force it to stay positive. Or else when we would derive it, we could get something that didn't work. So that's just one thing we have to make sure to do a little differently. And then we have our plus c. Okay, next, let me show you this one, just kind of practicing our exponent rules. So here, again, we've got to bump it to the top, but a common mistake is people will bring the 2 up as well. 2 isn't technically being cubed, only x is being cubed. So I'm going to leave the 1/2 and then bump x to the negative 3 up. And then when I go to integrate, the 1/2 tags along. Add 1 to the power, divide by that new power, plus c. And then I need to bring that x part down, so this will end up being 1 over negative 4 x squared when I combine those fractions. All right, the next one to show you. All right, there's good news and bad news. Back when we were learning how to derive, we had some sections on product rule and quotient rule. Okay, good news is when we're integrating, you don't have to memorize a product rule. There's not a product rule to memorize for integration. Bad news is there's not a product rule in integration. We've got to manipulate it in some way so we don't have a product. So any ideas? What could we do with that to get rid of our product? Yeah, we've got a FOIL. So then we get 3x squared plus x minus 2. And then we just have 3 terms. So we'll have 3x cubed over 3 plus x squared over 2 minus 2x plus c. And then we could cancel those 3's out and just have an x cubed. All right, now, next one I want to show you, x plus 1 divided by the square root of x. So when we were learning how to derive something like this, do you remember low D high minus high D low over low low? good news, bad news situation again. No quotient rule for integrating, so nothing to memorize. But you've got to find a way to get rid of the quotient then. So there are two methods, and it really comes down to a matter of preference. So I'm going to show you both methods because some people just feel more comfortable with one or the other. Okay, first method we could do is we could divide each of them by that denominator. So x divided by square root of x plus 1 divided by square root of x. And then for us to move forward with that, we would have to simplify their powers. So this is technically 1 power and a 1/2 power. Do you remember what you do with those powers when you're dividing? Yeah, subtract. So a 1 minus 1/2 would mean that's x to the 1/2 power. And then this, there's nothing on top of that 1, so we can bump it up. That would be x to the negative 1/2. And then each of those are a power rule. I'm going to leave that side for a second. So one method, divide each of them by their denominator. The other method is you could take that numerator and then bump that denominator. Well, I got to bump it in a different way. You could bump it up, but if you bump it up, it becomes a negative power. So I could take that denominator, move it to the top, and then what you would do is distribute. So x to the first and x to the negative 1/2, you add their powers. So 1 minus 1/2 is x to the 1/2. And then 1 times x to the negative 1/2. And then we are in a matching spot. So it's kind of like whatever you feel more comfortable doing for the middle step. Divide each of them by the denominator or bump it up and distribute. But they'll both get you to the right spot. And then let's go ahead and find the answer. So we would add 1 to the power. So that would be 3/2. And then instead of dividing by 3/2, I'm going to go ahead right away and multiply by 2/3. And then here, add 1 to the power, so that'll be x to the 1/2. And then instead of dividing by 1/2, I'm going to multiply by 2 plus c. Your mind spinning? This is one of those things, just like kind of when we first learned how to derive. It's one of those things where repetition will help you get better, quicker, more comfortable. It's just a bunch of rules to memorize. Right now, there's not really a concept with it. It's just one of the computation parts of calculus. We just got to practice the rules. And so that's what we'll kind of be working on in this section. And we'll kind of just get better at this and get better at integrating. Any overall questions right now on that part? All right, then I am going to pass out your tests so you can see those.